as I said, my name is Javier Campos. I head the data labs within Experian UK&I, and just to describe what the data labs are, it's a bit like the R&D part of Experian. So my team job is to create the next generation of products. Today I'm gonna, so part of my job is to constantly be looking at the new technology, new developments on pretty much the industry, society, and see what can actually be applicable to, in this case, the Experian or the financial services industry. So today I'm going to talk a little bit about quantum computing and give you an overview. Very complex topic, but it's fascinating, and it's been recently on the news, so hopefully quite topical. So if I start on the deck, let me see. The first one, you can actually see the agenda. So we're going to go very quickly about what is actually a quantum computing. I'm going to also tackle at the beginning quite a few myths, and probably if I ask some of you, you might have heard from the news some things, but just to say what is true, what is not true. Then we're going to go into the detail. How do they work? Then I'm going to talk a little bit more concrete into what is going on in the industry, the ecosystem. Believe it or not, you can today program a quantum computing. They got their special programming languages. They're actually also available in the cloud for some computers, so you could start today. And finally, we'll touch a little bit of the applications, and you can see why for some areas this is a big topic, but some areas, and you will see this is part of the topic. So the first question is, what is a quantum computing? And this is when some of the misconceptions actually start. People say, oh, quantum computing is, you will see there are some definitions. It's a machine that uses property of quantum mechanics, quantum physics, to store data or do computation. Why is a bit misleading? Actually, any computer you have there, not just on your phone, on your car, on your laptop, and they use transistor, and transistors actually, for those that know a bit the electronics, use something which is called the PN sort of junction, which use quantum tunneling. So actually, all our computers, even our mobile phones, even any these days any appliances, even your washing machine might actually be a quantum device. So it's a bit we need to be a bit specific. So what a quantum computing is not just using quantum effects. As I said, all computers that have any transistor will use it, but specifically the way they storage and process information. And they use what we call qubits. And this is the critical thing for a quantum computing. What is actually in a normal computer, which I'm sure you all know as developers, actually the binary, the bit, which is the smallest unit of information, can contain 0 or 1. By doing this, then you scale, you create all the gates that do some processing on the information, and then you build our current generation of computers. Quantum computing is very different. The way they store information, and that's where the magic actually lies, is actually, it can as well be 0 or 1, but it can also be something in the middle. So for example, if you were compared to a switch, a light switch, a normal computer will be a switch that you move on and off, versus a quantum computer is like a dimmer, can actually be in the middle. And that creates quite a lot of interesting things. So the first thing is quantum computing, it actually stores information in qubits. Now, this is the important one, some of the myths. The first one, people are saying, and even the press get this wrong, by the way, which is quite embarrassing. And I saw an article in the New York Times, which I think they changed it. But first one is quantum computer are very fast classical computers. That actually is false. In fact, for many operations, a quantum computing is much worse than a normal computer. Anything that requires a lot of I/O, quantum computers are really bad at that. And a classical computer will outperform it. So that's false. Second one, quantum computing means the next generation. So once the quantum computers are working, the current generation is not going to be around. Well, this is also false. Why? Because quantum computers, and you will see, they do certain things very, very well, but not everything. And it is very likely that in 10, 20, 30 years in the future, you will have both types of computer, classical computers and then quantum. Next myth, quantum computing will destroy cybersecurity. And this is where people say, oh, once you have a quantum computing, you can actually break any website in seconds, any visa encryption, whatever, HTTPS, which is based in a RSA sort of type of algorithms can be cracked with quantum computer. This is a bit both true and false. It is true with a quantum computing, you can actually break any encryption that today, if you look at today encrypting and you get a very long key, like 1,000 bits or 5,000 bits, a brute force normal computer will take many years to break it. A quantum computer can break this very quickly. So it is true that a quantum computer will break the current cryptography, but it's also true that you can introduce new cryptography that will substitute. So effectively, yes, you can replace the legacy one, and once quantum computing are available, RSA algorithms will stop being used because they will be break very quickly, but there are already things either using quantum or not that cannot be there. And you will see why that's the case. The next one is, a myth is what people are saying are going to be there in the next 5 years, 10 years. If you talk to the vendors, they will tell you next year. Well, the point is, we don't know. Actually, it is quite interesting. IBM just announced a couple of days ago that they released the 127 qubits, which is a big deal because with that sort of level, until then, only the biggest quantum computer had about between 50 and 70 qubits. Going to 127, which is actually double, that's starting to get the scaling. And what is exciting is, as you know, because computing the way it works, it's going to scale. You need, for a practical computer, 1 million qubits, by the way. So you still feel away, but actually, because of the exponential, we're not going to need 10 years. If we keep, and this IBM announcement is a bit surprising. It was a bit earlier than expected. So if this keeps going the way it's going, we're going to have a quantum computing available in a few years. The next one, which is a bit for these Marvel fans, quantum computing world, whatever. And if you actually do a bit of a search, there are quite a lot of stuff on the web. People are putting, you can use to do time travel, synthetic consciousness, a lot of weird things. And actually here is unlikely, but not quite there. Quantum computing and quantum mechanics is quite strange, and you can argue we still don't control. So what is possible is there. So this is the next thing is quantum supremacy. You probably saw that happen last year when there was a lot of, what is the quantum supremacy? Is when a quantum computer can perform an operation much faster than a classical computer. That was achieved, it was a bit controversial, by the way, but it was sort of achieved last year. Google claimed they did it. IBM published a paper saying, well, you sort of cheated. They say, well, this computation, a classical computer would take 120 years. IBM came, actually, you can do it using other method in 3 days, something. So not quite supremacy. But the point is, and actually, that was with 50 qubits. With 127 qubits, that is now absolutely out of the question. A quantum computing for a specific type of problems can massively outperform classical computers. And you can see here there. So why does it work? Well, at the heart of why this, the quantum computer does all these amazing things for, and you will see I make a lot of points only for a specific type of problems, is the quantum mechanics. The first one is quantum mechanics. The way it works is the measurement problem, which in quantum mechanics, you have every particle in the universe have what is called a wave function. The wave function is something linear, is something that the mathematics works, evolve to certain evolution. But then what happens is when you measure, the whole thing collapses into only one. So effectively, before you measure, you only have probabilities. This is very, very weird because in classical mechanics, if I throw a ball, I know exactly the position of the ball and the speed at every trajectory of if I fire a rocket. That's in classical mechanics. Quantum mechanics doesn't work like that. If I throw a ball, I will know the probabilities. And by the time I measure in a specific point, then the function will collapse and I will change, which is actually quite mysterious. We don't know why it happened or why not. We just know that it works and it's been very successful. So one is the measurement problems. The second one is the superposition, and this is also very, very weird. So if you throw a single particle like a photon, you throw them in, and there are two slits very close. You throw them one, and they actually show interference pattern which is the same you do with wave. Why this is weird? Because actually that happens if you shoot them one at a time. So you shoot one, one, one. All of them show like they interfere each other. This is quite strange, and we don't have time to go into the detail explaining. This also provide, well, you probably heard of the Schrödinger cat, that a cat is dead and alive at the same time. This effectively what happens is, which is the superposition. When you have two functions, and if you remember what I was saying, when I throw a ball, I don't have the specific function that says that's the ball. In a quantum ball is not like a normal ball. It's got a distribution. It could be in a number of places, and it could have a number of speeds. It's like a distribution globally. On the Schrödinger equation, and the paradox is you put a gas in a box, and then you sort of get something to decay, a reactive material, which a half-life, which might or might not decay. You don't know. And the problem is, quantumly, from the quantum point of view, the cat is half-dead in a life, and you only know when you open. When you open the board, then you collapse because you measurement, and remember the measuring problem, and then things take one thing or the other. All very strange, and there are few interpretations, some of them the multi-word, but we don't have time to go that. And for me, this is the really weird one. This is the one that actually Einstein got wrong, which is the entanglement. And this actually, I think, is one of the key there that is going to make the quantum computer so powerful. So what happens is you get two particles. You actually get them in sort of sharing the same state, and then you send them away. And this is the key there. You send them many light years away, and then you measure one. When you do that, immediately the other will change. But the amazing thing is that doesn't happen. It only happens when you measure. And because if you send them very far away, that means that the information or whatever is happening travels faster than light, which it could not happen according to Einstein theory. So again, really fascinating thing, and you can have some graphics there. We don't know why it happened, but we know it actually happens. So this spooky action as a distance, that entanglement from particles, can actually be used also in quantum computing. So how do the quantum computing works? And without going in a classical computer, when you do a calculation, the computer has to do every calculation at the same time. In a quantum computing, that's not the case. What happens is, because of you create these probabilities, and so the information is stored in the qubits. Remember, the sphere is not just 1 or 0, it's a vector. And this is the trick. That vector can be negative. And so effectively what happens is, when you calculate the potential solutions for a particular problem, a quantum computing, these amplitudes, sometimes they interfere each other. And when that happens, what happens is, a classical computer has to perform all the calculations and have to do it. So it will take these hundreds of years. But a quantum computing does this interference and cancellations, and you will see there. And that's how it actually can come to the solution faster, because these probabilities, again, a negative probability, classically don't try to understand it, but the point is it gets there. And if you only remember one thing, is this one: quantum computers are not faster in terms of quicker than classical computer. What they do is, for certain type of problems only, they do the calculations they get to the solution much quicker, because they can interfere. They can do interference between all these solutions, the same as if you remember when the photon was sending to the two split lines. Here is a similar effect, and they get to the right position much quicker. So how to build, and I'm going to accelerate. I think I'm running a bit late. This is, again, I could spend hours. There are many ways of doing it, and there is at the moment a really race, and actually the military is involved, so the US, China, and people are backing different technologies. Some people are doing it using trap ions, which is the one that you see at the top. IonQ, I think, is the only one that is in the stock market, if anyone wants to take a look at that. And they are doing quite well. All these things have pros and cons. So one is trap ions. The one that Google and IBM use, this is superconducting qubits. The problem with that one is you need very, very low temperatures, close to 0 Kelvin. So effectively, when you see the pictures on the news, is massive. Then another way, which is using photons and light, and this is using lasers. that the advantage for that, you can do lasers at room temperature, which is great, but the size is astronomical. So for example, China is doing that, and they just announced not long ago, like a computer doing 60 qubits with that one. Why is so challenging then? Why we can do one? Well, the main problem is when I was explaining about all this magic of quantum physics, why don't we see that in reality? I was talking about a ball, but when you throw a ball, the ball, then they are in a single state, you can measure the speed there. Why don't you see? So we don't see quantum mechanics in real life because there is something called decoherence. When all this entanglement and all these things I mentioned, when you get a normal temperature, all these things collapse and they don't happen. For these things to happen, it has to be very, very specific condition. And to do that is very difficult. That's why the quantum fault tolerance is quite tricky. So there are enormous engineering challenges to build these things. And to be honest, the fact we have 127 qubits already is incredible. So these things, fault tolerance, decoherence, really difficult. So in terms, was said before, actually you can already, there is a quantum computing marketplace. Your favorite software cloud, if you go to Amazon, you go to IBM, to Google, Microsoft, they all have some sort of quantum cloud that you can actually get and book some jobs in a quantum computing. You need a special programming language, which is, you have to use, in the normal computer, the way you can do a program language that eventually is a compiler and gets to effectively switching on and off the gates at the AND and all this. Quantum computing, these gates, you have to, at the moment, the programming languages are a bit more complex and the algorithms are a bit more complex, but this will get like the same that happened at computing, So, there's what is some of the last developments. One of the things I just wanted to, and this is again, is being shown quite quickly, is a time crystal, which, if you follow Star Trek or Marvel, some movies, they do it, but actually they exist in reality. This has been a shock for all the community. What is a time crystal? Well, they're saying if you look at a crystal, is called regularity in space. So a diamond, you look at diamond and the atoms are structured there. They're saying a time crystal has the regularity over time. There are many, many implications, fascinating. We can use them. Okay, I'm gonna accelerate very quickly because we're running a bit late. So this is the key there is from all the potential problems where we can actually, and you can, here, this is the mathematical, the NP complete problems really hard, the P, which is where most computers can do this very quickly. So we think quantum computing can do much more than computers, but for example, factoring is included, but we don't know how much. And also, there are many problems that quantum computers don't do better than computers. There are some things here, for example, which computers can run very well. So the point is, a quantum computer will not have any advantage over a classical computer, and that's the point. So the first, just there. So what are the potential, some of the first application in cryptography is an absolutely good one. You could actually you will need to create a new type of cryptography because, as I said, anything that is based in RSA, which is based in factoring, a quantum computer will break instantaneously. Then two things in medicine, this is why pharma is putting a lot of money here. You can use this to simulate a quantum system, which guess what is what the drugs are. So that's what they will do that, machine learning, and then also searching some of the type search. So three things very quickly, and then I will leave some time for questions. What are the things you can take from the section? The first one, where are we in the quantum computing journey? Very, very early days. If you think about in the 50s, the first computer, in the 40s, which were ENIAC or the ones in the UK, there was a massive run and the processing power was pathetic. This thing will take 30 seconds. Well, at the time it was amazing. Look, this room full of devices can do what a human in 20 hours. That was unbelievable. Quantum computing is the same, but then you look at how this evolved. Now all this computer power, you have it much more in any iPhone. And not only that, if you look at the faster computer today, which by the way is a computer in Japan called Fukayo, have 442 teraflops, which if you computer is absolutely amazing. So you can see the computer is going to have the same evolution. When you see the current computers now, they are run, massive, expensive. They have a lot of errors, the same as the early ones. We will have them, and what will happen in the same time period remains to see. Second one, and please take away, because this everyone, especially journalists, get it wrong. Quantum computing just doesn't do things in parallel. No, that's not the case. What it does is a lot clever to pruning, if you look at it in the language of trees, in terms of the searches and everything, when it gets to the potential space solution, prunes the wrong ones and get to the solution much, but it gets quicker because it gets to the right solution in one go, versus the classical computer have to try everything. So the gains on the computer comes from the interference. It doesn't come from there. And how to get started? Well, I leave there some books. As I said, the quantum computer book is quite good, but a bit harsh if you mathematics are not a bit out of scratch. But really beautiful book, for example, for quantum mechanics, something deeply in Hadi from Sean Carroll and Roger Penrose. This also does a lot of things. So yeah, so final point, and then we go to questions. You might get confused and say, well, I don't really understand what you're talking about. What you mean, cat dead and alive? Well, don't worry, nobody is very, very weird. And actually, this is a Nobel Prize, one of the best physicians we have, American. Nobody can tell you that understand this, because it's so not like our intuition work. And thank you very much. I'll leave to questions.
Thank you, Javier. Well, the question here is that I have is actually, we are talking about quantum computing for several decades, and you actually mentioned something about when you see, but when we see we can start using them widely. But can you speculate when we can start using them?
Thank you. That's a very, very good question. I mean, if you could have asked me 2 years ago when this is going to be ready, and I've been looking, I have 2 degrees. One of them is in quantum physics, in quantum fundamental physics. So I've been looking at this for a long time. I would have said we are still 5-10 years, because the engineering problems, I cannot stress how difficult, to achieve these things, the entanglement, the superposition, which you need to calculate to do the quantum calculations and the interference to all these things they need so precious and special conditions to scale this. And if you think about the current computers, they need to be at room temperature. They need to even have be able to work and function at 30-40 degrees. Is a massive engineering project. So if you could have said 2 years, I would have said 5-10 years. But now is really incredible, and especially IBM is a bit earlier than expected. So now I will say maybe between 3 to 5 years, we might be able to see this thing. You only need 1 million qubits to start really being able to do practical things. And actually 3 years is a lot sooner than when you think about it. So we might start seeing this. You can already today run some quantum calculations on the cloud, but those are simulated, but you can get away. But in about 3 to 5 years, I think we will see these things commercially and being applied by, as I said, especially pharma. They're going to make massive value to the drug discovery and cycle. Today to develop certain drugs takes like a decade. By the time because all the interaction between the molecules are very difficult, so you have to do all the different tests how you can do the component, for example, designing antibiotics, and it takes a long time, and then you have to go to human trials. This thing can simulate the actual quantum system, so you could really compress. So this for medicine, it will be amazing, and that's why, as I said, the pharma is putting billions, out of all the money going into that, which I think this year there will be about between 50 and 100 billion. And know how much money is there is always difficult to calculate for many reasons. But this investment is not, this is not like something in a lab lock away. It's quite a big thing.
Okay, it's quite promising actually. So thank you very much. I hope you'll see you in a couple of years when you can give us example using quantum computing. Thank you.
Thank you.